Welcome back to this next video in which we are discussing composition series and the Jordan-Hőlder Theorem. Okay, so we're currently in the process of trying to prove part 2 of the Jordan-Hőlder Theorem, which remember says that if we have a finite group and we have two different composition series for a finite group, then there is a correspondence between these two different composition series. Namely, the lengths of these two different composition series will be the same. And in addition, if you were to list out the composition factors for each one of these, that list of composition factors would be the same for both of these composition series. Okay, so if you did produce these list of composition factors for each of these composition series, the groups that are in it might not appear in the same order, but overall each of the lists will contain the same groups the same number of times. Okay, right. So to prove this, we are doing a proof by induction, okay, on the order of the group. So we've shown that it is obviously true in the case where the order of the group is equal to 1. We then assumed that it was true in the case where the order of the group was less than some n, and we now want to prove that it's going to be true in the case where the order of the group is equal to this n. Okay, and we've firstly addressed scenario 1, which was where the group was a simple group. Okay, and in that case, there's only ever one composition series for your group, because the only maximal normal subgroup that you have is the trivial subgroup, and therefore you're always just going to have this composition series as the length 1 composition series, where the two subgroups appearing in that composition series are just the improper subgroup and the trivial subgroup. Okay, and therefore part 2 of the Jordan-Hőlder Theorem is trivially true. So we've then taken on scenario 2, which is that the group of order n is not a simple group, and therefore we can assume that the composition series that we have for this group are not of length 1, they have length greater than 1. In particular, that they will always at least involve one other subgroup that is not the trivial subgroup or the improper subgroup, i.e. this subgroup that's to the left of the improper subgroup, gk-1 and hl-1. We have then split this into two cases. Firstly, the case where these two maximal normal subgroups in G that appear in the composition series are the same, so gk-1 and hl-1 were the same, and then we've shown by the induction assumption that will then imply that the second part of the Jordan-Hőlder Theorem will indeed be true. What we now want to do is take on the harder case, which is where these two maximal normal subgroups are not going to be equal to one another. So case 2, we now assume that in these two different composition series here, we have picked different maximal normal subgroups as our subgroups that will be just to the left of the improper subgroup. Okay, so i.e. gk-1 is not equal now to hl-1. They are different maximal normal subgroups in the group capital G. Okay, and we still want to prove that the second part of the Jordan-Hőlder Theorem is going to be true, i.e. that the lengths of these composition series are going to be the same, and that the composition factors are going to correspond. Okay, so firstly then, what we're just going to do is a bit of setup. So initially, what I'm going to do might seem a little bit unmotivated. You might not see how it's going to actually end up proving the second part of the Jordan-Hőlder Theorem, but we're going to need all of what I'm doing now to actually be able to complete the proof. Okay, so this is setup, so just bear with it. Okay, right, so the first thing I want to do is consider the product of these two maximal normal subgroups. So I want to take the subgroup product of gk-1 and hl-1, and my aim is to show that this is actually equal to the entire group capital G. Now how am I going to do that? The way I'm going to do it is I'm going to show that firstly this product that you get here is a subgroup of G. That's very easy. I then want to convince you that it's going to be a normal subgroup of G, and it's going to be a normal subgroup of G that will contain both of these subgroups gk-1 and hl-1. Okay, and since those are maximal normal subgroups, that must imply that this is the improper subgroup. Okay, so I'll repeat all of that now slower. So firstly, the first thing to say is that this subgroup product of gk minus 1 with hl minus 1, it will end up being a subgroup of capital G. And the reason is that the two subgroups that you're producting together here are both normal subgroups. In fact, we know from our study of the product of two subgroups, in the video on the product of two subgroups, that you actually only need one of them to be a normal subgroup. If just one of them, for instance, HL minus 1 was a normal subgroup, then it doesn't matter about the other one. You will end up, when you product these two together, with a subgroup of G, i.e. rather than just a subset of G. Okay, so we know instantly, therefore, that it is a subgroup of G. What I want to now show further is that it's actually a normal subgroup of G. Now this comes from the fact that both of the things that we have producted together are normal subgroups of G. Okay, so how am I going to show this? So what of course I need to do is show that no matter what element of the group capital G I use to conjugate this subgroup, that I'm going to get the subgroup back. So if I was to conjugate it, so if I was to take G and then conjugating gk minus 1 producted with hl minus 1, G inverse, I need to show that I will just get this subgroup back again, gk minus 1, hl minus 1, for all little g is an element of the group capital G. Okay, so this is what I need to show in order to conclude that this is indeed a normal subgroup of capital G. Okay, now remember I'm working in the finite case here, so proving this is quite easy. Because in the finite case, all you actually need to show in order to show this is that whenever I take an element from this subgroup here, that it's, when conjugated by little g, it's going to end up back within the subgroup. Now let me just create some notation for elements in this subgroup. So let's just create some notation then for the elements of the product of gk minus 1 with hl minus 1. Okay, so remember this consists by definition of all of the elements of the form little h1 composed with little h2, where little h1 is an element of gk minus 1 and little h2 is an element of h, and I'll try and fit it in, l minus 1, and then close the set brackets there. Okay, so that's just the definition of the product of two subgroups, and we know that because of the fact that one of them, in fact both of them in this case, but we only need one of them to be a normal subgroup in order for this to end up a subgroup itself. Okay, right, so now I've got my notation for the elements here. I claim that it will be enough to show that for all of the elements that I take here, i.e. for all little h1, little h2, if I conjugate it by g, I will end up with something that is back in gk minus 1, hl minus 1. And let me just remind you of the reason for that. Remember that you can use little g, this element from the group capital G, to conjugate the entire group capital G. Okay, and it will be an inner automorphism. It will define a bijective map from all of the elements of the group capital G to elements of the group capital G. In particular, it will be injective. Okay, so if you then limit it to this subset of G, which is the product of gk minus 1 with hl minus 1, it will still be an injective map. If you can then show that all elements on this subset are mapped back into it, okay, then you can conclude that this map, restricted down to gk minus 1, hl minus 1, is a bijective map from gk minus 1 to gk minus 1, hl minus 1 to gk minus 1, hl minus 1, because of the fact that we know it's going to be injective from the fact that it's an injective map on the entire group. All of the elements here are being mapped back onto there. Okay, and because everything's finite, if we've got an injective map where we're mapping everything from here into here, okay, it must also be surjective and therefore bijective, i.e. you must get the entire set back again. Okay, it would be more complicated if we were working with infinite group theory, because then, even though it was injective, you would be uncertain as to whether it was bijective, because you can have injective maps from a set to itself that aren't surjective. If you're working with an infinite set. Okay, that's one of the major things that you have to get used to when you're learning elementary set theory. Okay, right. So all I need to show then is that any element in here conjugated by any element of the group capital G is going to give me another element in there. Now why is that going to be true? Well, of course it's going to be true because GK minus 1 and HL minus 1 were normal subgroups. So clever trick here, just insert in between little h1 and little h2 G inverse composed with G. Okay, like so. That's perfectly valid to do because, of course, everything obeys associativity. That's why I haven't bothered to put brackets in here. Okay, but I could put brackets around G inverse G here and I'd just get the identity, and therefore that wouldn't change anything. Okay, so this is equal to this, but of course, if I conjugate little h1 by an element of the group, I'm going to get something else in GK minus 1. So remember, little h1 is an element in GK minus 1. Because this is a normal subgroup of G, okay, I'll just make sure it's in view. Yes, it is. Up here, it's a normal subgroup of G, a maximal normal subgroup even, but we just need that it's a normal subgroup at the moment. We can conclude that this will be some little h1 bar here, some other element GK minus 1 here. Okay, so that's fine. And this one here, of course, again, because HL minus 1 is a normal subgroup of G, when I conjugate little h2, which is an element of capital HL minus 1, by little g, I'm just going to get some other element of capital HL minus 1, which I'll call little h2 bar. Okay, and of course, this is an element of GK minus 1, this is an element of HL minus 1, so of course, when I compose them together, which is what I'm doing here, so this is just compose these two together now, I will still end up with something that is in the subgroup product of GK minus 1 with HL minus 1, and hence the proof is complete. Okay, so indeed, this is going to be a normal subgroup of my group capital G because of the fact that the two subgroups that I am producting together here are normal subgroups in G. Okay, excellent. So we now have that GK minus 1, subgroup producted with HL minus 1, is indeed a normal subgroup of capital G. Now, obviously, it will contain GK minus 1 and HL minus 1 properly. Okay, so I'll write this out. So GK minus 1 will be a proper subgroup of the product of GK minus 1 with HL minus 1. Now, I don't even need to state it for HL minus 1. This is enough to make the conclusion that I need, but you could state the equivalent thing for HL minus 1 here. Okay, it will be a subgroup, that's obvious, because you could just set little h2 here equal to the identity and you'll get all of the elements of GK minus 1 there. Okay, it will also be a proper subgroup because it will contain all of the elements of HL minus 1 here, and some of the elements of HL minus 1 are not in GK minus 1 by the initial assumption that they were different. Okay, and therefore this one will be properly contained in here. So look, I've now got a contradiction, well, an apparent contradiction, because this is a maximal normal subgroup, but I now have a larger normal subgroup inside of G, so that forces this to be equal to the improper subgroup. So therefore, we can conclude that the subgroup product of GK minus 1 with HL minus 1 must indeed equal the entire group capital G. Okay, so that's the first little piece of setup that I need you to understand, that when I subgroup product these two different maximal normal subgroups of G together, I'm going to get the entire group capital G. Excellent. So let's just draw a little picture of this. So we'll draw a little box here, and then we'll look at the other important piece of setup. Okay, so this is my entire group, capital G here. So I'll colour this in orange here, like so. And then I'll just move this up a little bit. Let's draw on GK minus 1 and HL minus 1. So this is GK minus 1 here, and let's say this is HL minus 1. Of course, they will have a non-trivial intersection. At the very least, they'll have the identity in their intersection here. Okay, so here in red is HL minus 1, and here that's having green, this is GK minus 1. And now I'm saying that if I take the subgroup product of these, which of course you can view as being all of the left cosets of HL minus 1, which contain elements of G, okay, GK minus 1 rather, okay, so you'll do this, you can partition the entire group capital G up into the left cosets of HL minus 1, after all it is a normal subgroup, okay. Well, you can do that anyway, but okay, you don't need it to be a normal subgroup. That was a mistake saying that. Any subgroup, you can partition it up into the left cosets. It being a normal subgroup will mean, of course, that the left coset partition is the same as the right coset partition. Okay, so I can partition up G into the left cosets of HL minus 1, and what I'm now saying when I take the subgroup product of these two is that I want all of these left cosets of HL minus 1 that contain elements of GK minus 1, okay, and from this result it must be the case that every single coset contains an element of GK minus 1 here. Okay, now note another interesting way of looking at this. We know that whenever the subgroup product is indeed a subgroup, from the video on the product of two subgroups, we know that this implies that it's equal to what you would get if you did it the other way around. So if you did HK minus 1 and product it with, oh whoops, I'm getting a little bit confused here, HL minus 1, and then producted it with GK minus 1. So these two sets are exactly the same. So the other way of viewing this is that it's the left cosets of GK minus 1 which contain elements of HL minus 1. So you could quotient your group up into the left cosets of GK minus 1 and take those cosets that contain elements of HL minus 1, and again that will equal the entire group, capital G. And it's important that we have these two different interpretations of how we actually build this, and it will become important in a moment. Okay, right, so be aware that there are those two different interpretations of how we've actually built this, and of course we're ending up with the entire group here. Okay, right, so what I now want to do, just to finish this setup, is talk about another thing. I want to define a new thing. So I'm going to define F to be the intersection of these two maximal normal subgroups. Okay, so F is going to be the intersection of GK minus 1 with HL minus 1. Okay, so on this picture, it's this portion here. And of course, we know that that is always going to end up being a subgroup of the group capital G. Okay, so F is going to be a subgroup of capital G. What I also claim is that F is actually going to be a normal subgroup inside of GK minus 1 and inside of HL minus 1. So I just want to show you this right now. So F is going to be a normal subgroup inside of GK minus 1, and of course it's also going to be a normal subgroup inside of HL minus 1. Okay, and I can say that it's going to be a proper normal subgroup. The reason I can say that it's going to be a proper subgroup is that there must be elements in GK minus 1 that are not in HL minus 1. Okay, if all of the elements of GK minus 1 were in HL minus 1, then this would be contained within this, which would contradict this one being a maximal normal subgroup. Okay, so all of the elements of GK minus 1 cannot be inside HL minus 1, and the equivalent argument holds the other way round for HL minus 1. That there must be elements in HL minus 1 that are not in GK minus 1. Okay, so it cannot be the case that one is completely contained in the other, and of course they're not equal to each other by the initial assumption, so the intersection is going to be a proper subgroup of both of these. Okay, now why can I then argue that it's going to be a normal subgroup of each of these? Well, of course, I know that each of these is a normal subgroup in capital G, so let's take this case here firstly to argue. Okay, so here is F on my picture. I'll just colour it in firstly. So there's F. Okay, so what I want to now prove is that if I conjugate F by any element of GK minus 1, so if I consider GF G inverse, okay, I want to prove that you get F back again. Okay, no matter what little g you pick from inside GK minus 1. Now, why is that going to be true? Well, again, because we're working in the finite case, it's sufficient to prove that if I conjugate any element of capital F by little g, I get something that's back in capital F. So all I need to prove is that G little f, G inverse, is an element of capital F. Okay, so why can I do this? Well, the reason is that I know that HL minus 1 is a normal subgroup inside of G. Little g, which is an element of GK minus 1, that is ultimately an element of capital G. So I know that if I conjugate any element of capital H L minus 1 by any element of the group, I must get something in capital H L minus 1. Okay? little f is an element of HR minus 1 because it's in the intersection of the two, so it must be in this yellow bit here. Okay, hence when I conjugate little f by g, I must get something that's in HR minus 1. Also, I know that I have to get something that's in GK minus 1 because this is a subgroup and everything that I'm composing here is in GK minus 1. So I know that this is going to be in both of these. It's going to be in GK minus 1 and HR minus 1, and therefore I can conclude that it will be in the intersection of the two. And the exact same argument works for why f is a normal subgroup of HR minus 1. Okay, you just have to change everything around. Okay, so instead of using the fact that HR minus 1 is a normal subgroup, you'll have to use the fact that GK minus 1 is a normal subgroup, and therefore when I conjugate f by anything in HR minus 1, I must get something that's back in GK minus 1, but because HR minus 1 is a subgroup, I must also get something that's in HR minus 1, therefore it must be in the intersection of the two. Okay, so this is the argument as to why this intersection of GK minus 1 with HR minus 1 must be a proper normal subgroup of both of these. Okay, so I hope you understand why it has to be a normal subgroup and why it has to be a proper normal subgroup. Okay, right, the final thing then to do in the setup is say that because f most certainly has an order less than g, okay, so it's certainly going to be a finite group, what I can do is devise a composition series for it. Okay, so let's have this here. So I'm just going to write out some notation then for the composition series of f. So we'll have the improper subgroup called fm here. Okay, and of course it will have a normal subgroup which will be fm minus 1 here. And then we'll go all the way down. I'm doing this backwards. I'll start over here. Here's the trivial subgroup, which can be called f0. And then it will be normal within f1, and then it will go all the way up like so. Okay, so I've just found you a composition series for the intersection of these two maximal normal subgroups, GK minus 1 and HR minus 1. Okay, so this is just some arbitrary composition series for this intersection here, and we will use this in the next video to actually end up proving part 2 of the Jordan-Hőlder Theorem for this case 2 where the two maximal normal subgroups are not equal to one another. Okay, so we'll continue with this in the next video.